Good afternoon. This is Dr. Jingbo Louise Liu. We are going to discuss Chapter 3 about alkane and cycloalkane. Today, our major topics will be the conformations and stereoisomers. So first of all, let's see if we have First of all, we need to know conformation analysis. We are going to use ethane as the example. What is the conformation? Conformations are the different spatial arrangement of a molecule, which are generated by rotation of the carbon-carbon single bond. Confrontational analysis related to the study of how conformational factors affect on the structures of molecule and associated properties. For this conformation, we need to know three key points. Number one, conformation are the different spatial arrangement for the same molecular formula. Number three, the conformation are generated by rotation of a single carbon-carbon bond, such as this red-colored carbon and second red-colored carbon. And these conformations can be represented by three different forms. So first one, you can use wedge and dash structure to represent a conformation. Second type is called sawhorse structure. So again, you put the carbon and the carbon, you bonded them together. You have one carbon in front, another carbon in the back. So you are going to draw a projection. The third one is called the Newman projection. The Newman projection is more commonly used for us to determine or to represent the conformations. How we are going to complete a Newman projections. And from the Newman projections, so how many different conformations we can draw, and then which of the different conformations are more stable. So that's what we are going to learn for the Newman projections. In order to complete a Newman projection, we are going to follow 4 different steps. First of all, in the Newman projection, we are going to set down the carbon-carbon bond. So you are going to place a point for the front carbon. The front carbon behaving like using a point, a dot to represent the front carbon. And then you use a circle to represent the back carbon. And then each carbon has 3 other bonds which are going to be placed symmetrically around that carbon. So the front carbon, you simply connect that point and draw a single line to represent the carbon single bond. And then the back carbon, you are going to use the bond which is sticking out of the circle to represent different bonds. And then for your Newman projections, particularly for this ethane, you can write it down. You can write down different structures, infinite structures, when you rotate it by different angles of the carbon-carbon single bond. However, 3 major structures are normally used for study. The first one, front carbon, back carbon, they both connected to the hydrogens, both hydrogen located in an overlap position. So this case, you call it eclipsed conformation. In this eclipsed conformation, you have an angle which is called the torsional angle. Torsional angle is between the carbon, hydrogen, and the carbon, back carbon and hydrogen. That angle, if that angle is 0, you call the torsion angle 0. Corresponding structure you call the eclipsed. Imagine you are going to rotate your carbon-carbon bond. The front carbon you rotated by 60 degrees. What's going to happen? Your torsion angle will be 60 degrees. In this case, the structure is called gauge structure. If you continuously rotate this carbon by 100 degrees, so this hydrogen, this pink hydrogen, front bonded with front carbon, you rotate it by 180 degrees, you are going to receive a structure which called anti-structure. So therefore, you are going to be more focusing on the angle between the front carbon hydrogen and the back carbon hydrogen bond. That angle you call it torsional angle, or also called dihedral angle. And which of these three different formula or conformation has the lowest energy? So normally you are going to use two structures. The one you call eclipsed carbon, hydrogen, hydrogen, carbon. They have a zero torsion angle. That structure has the highest energy. So that structure is related to eclipsed. And then the other one, so hydrogen, carbon, carbon, hydrogen, carbon, hydrogen, that bond is 80 degrees. So in this case, you call the staggered structure, or also called anti-structure. That staggered structure meaning, so your carbon, hydrogen, the torsional strain and also steric hindrance will be mitigated to the smallest one. In this case, this staggered conformation is the most stable one, which related to the better electron delocalization. Electron delocalization will stabilize the staggered conformation. The conformation which is not staggered, normally you are going to subject to the torsional strain. So in this diagram, the red colored hydrogen is the one you are going to rotate it. So again, between the staggered and the eclipsed structure, you have about 12 kilojoules per mole in difference of the energy. Again, the staggered structure is more stable. Your conformational analysis for butane. If you have ethane, you only have 2 carbons. If you have butane, you have 4 carbons. So how you are going to determine the Newman projection? Let's do this way. So Newman projection, I suggest you are going to use number 2 as the front carbon, number 3 as the back carbon. Number 2, use a point. Number 3, use a circle. And this number 1 carbon, so you draw it symmetrically distributed around the carbon 2, the front carbon. So you have a carbon-carbon bond, carbon-hydrogen bond. Similarly, your carbon 4, you are going to connect it to your carbon 3, the bond sticking out from the circle. You have 2 more hydrogens, also the bond sticking out from the circle. This first structure, so you are going to see a bond angle, a torsional angle. Is no longer called bond angle because it's not really a same carbon. One is front carbon, another one is back carbon. That 2 angles are called the torsion angle. So these 2 methyl groups, they are going to apply hindrance. You call the steric hindrance because they have larger group, and also because of the torsion angle, you also have the torsional strain. So this methyl and the methyl is going to subject to the steric strain, meaning the structure is less stable. If you put the carbon 4 and the carbon 1 on the opposite position, this structure you call the anti-structure. In other words, this anti-conformation is much more stable than the other structure. So the reason for the structure stability are related to the 2 strains. Actually, totally you can say 3 strains. The first one is called the torsional strain. The second one called the steric hindrance. The third one is the combination of these 2. The torsional strain is the strain that results from the eclipsed bonds. If you have the bond, the front carbon, back carbon, that related bond has an angle. That angle is related to the different structure, particularly the eclipsed structure, also included in some gauged structure. And the steric hindrance resulted from the atom spatial distribution. When two different atoms are close together, so the steric hindrance will be occurring. And then this steric hindrance, also called van der Waals strain. Torsional strain and steric hindrance combination is called steric strain. So these three different strains are very important for us to know. For your butane, if you write it down the Newman projection, let's say you have this eclipsed structure, you have this gauge structure, you also have the one we consider, also you can consider these two, you can also consider their gauge. These two, the second group, they have 60 degree, the third group you have 120 degree. This case your torsional angle is 180. In this case you have four different possibilities. The most stable one is the staggered structure, or you can call it anti-structure. And the other gauged structures have lower energy, depends on the steric hindrance and also based on the torsional strain. So that's about the stability. If you have a higher alkane, so what are the conformations? Again, no matter how many carbons you have, first of all, you need to choose a front carbon, a back carbon. In this pentane, you may draw two cycles. So this is carbon 1, carbon 2, carbon 3, and then carbon 4, a point, carbon 5 will be another circle. You can draw two of them. But anyway, for most of the higher alkane, you can use this zigzag arrangement to represent different carbons. And there's another kind of alkane we consider the cycloalkanes. The cycloalkanes, meaning the alkane, they are going to form a circle. When they are forming a circle, for example, you have 3 numbered rings, 4 numbered rings, 5, 6, 7, 8, 9 different numbered rings. Based on this geometry, say for this triangle, your band angle is supposed to be 60 degrees. However, for your single bonded carbon, you have that sp3 hybridization, meaning you have a tetrahedral structure which is preferred. Tetrahedral carbon prefers bond angle which is 109.5. Therefore, your structure band angle and your tetrahedral carbon preferred angle, they no longer match each other. Therefore, you are going to result in the strain for the molecule. This strain is related to the angle. You call torsional strains. So how do you minimize this strain? So it's important. Therefore, most of the cycloalkane in the future, including cycloalkene, alkyne, they may not be a planar structure. Let's see. So we are going to show you several important different structures. Before we moving on to the structure, you may have another question. Which structure is most stable? Which molecule is most stable? You have 3 numbered rings, 4, 5, all the way to say 16 numbered rings. How do you determine the stabilities of each compound? So in this case, you are going to use the heat of combustion. The heat of combustion is a way for you to measure the relative stability of cyclohexane. Cyclo in this case is alkane. Normally, the smaller this heat combustion, the more stable for that related compounds related to the including in the future is regular alkane. About the cycloalkane, the smallest cycloalkane will be carbon 3, C3H6. So again, you have your carbon-carbon, they formed sp3 hybridization, and then the single bond will be formed. However, the single bond, when they formed by the 3 numbered rings, so you should have 60 degree. Tetrahedrocarbon is going to have 109 degree. Therefore, your band is found to be bent. So the bonds are called bent bonds. So in this cyclopropane, you are going to see an eclipsed structure. These 3 carbon, they are in the same plane, but you have very high torsional strain due to the carbon-carbon bonds. And all these carbon hydrogen, they are eclipsed. If you have cyclobutane, butane, you can do this carbon 1, 2, 3, 4. So carbon 1, carbon 2, carbon 1 to 3, you can form a plane. The last carbon will be lifted up to adapt a non-planar structure. This conformation you call the Packard conformation. The goal for this conformation, why your conformation start moving around, adapted a non-planar structure, because you want to minimize the torsional strain. And the third important alkane is the cyclopentane. Cyclopentane, just imagine by forming a planar cyclopentane, the band angle actually is about 108 degree. So this band angle and your 109 degree for your tetrahedrocarbon preferred band angle, very similar to each other. Therefore, you can form a planar cyclopentane. This is reasonably stable. And you also form another 2 different conformations. One is called envelope conformation. Your carbon 1, 2, 3, 4, they are in the same plane, and your carbon 5 slightly lifted up to form an envelope structure. So to make your band angle is more approaching to 109. The second structure, or you can say the third structure, is the half chair structure. You have 1, 2, 3 of the carbons, they are located on the same plane. The first one lifted up, the fifth one pointed down slightly. This envelope structure and the half chair structure, they can convert from one to another very rapidly. So the energy differences is very low. But anyway, by forming an envelope and half chair structure, so you do more or less release some of the torsional strains. Then we are going to more focusing on the cyclohexane-based structure. So I'm going to stop for now, give everybody a few minutes to a break,